Hi, class. In this section, we're talking about a technique called variation of parameters, which is going to help us solve the equation that we've been working with, our second order differential equation, linear with constant coefficients, um, with with a more general right-hand side, with our more general homogeneity. So what that means, let's just summarize a little bit of what we've learned about this type of equation. In first, we learned about the case where f of t equaled 0. So that was our homogeneous case. And we learned how to solve it in every case with the characteristic equation. And then the next case that we saw was some special cases of our right-hand side. So we learned how to do this in the case that, like, e to the RT or cosine beta t or you know t squared plus 3t plus 5, etc. So then we learned how we could sort of make a guess at what the solution was and then solve it, figure out, refine that guess using the method of undetermined coefficients. So now what we're going to see is a method that we can use for any right-hand side. So for an arbitrary f of t, and I mean, there's some limits we'll talk about, but more or less arbitrary, we can solve the equation using variation of parameters. And that's what we're talking about in this video here. So as you might guess, undetermined coefficients is usually easier than variation of parameters. So if you can do that, if you have one of these cases, one of the cases that we laid out in the table, then you can use this easier method. Variation of parameters is pretty cumbersome, but it's sort of useful to know that there is a method that's going to work for more or less any f of t. And that's sort of why we have to lay it out here. So really what we're after, here's what our goal is. We're looking for a particular solution, yp, to our non-homogeneous equation, which we're calling nh. And so the observation that we're going to make here is that we already know how to find a general solution to the homogeneous equation. And that's what I've just written out here. So that general solution is given by c1y1 plus c2y2, where c1 and c2 are constants. So our sort of guess here is that we know that we're not going to be able to use constants to kind of manipulate this formulation and end up with the right-hand side that's non-zero. But what if we could manipulate these things more so? Instead of using constants, what if we used functions of t here instead of the constants? Then when you take your derivatives and plug them into the left-hand side, maybe what you get on the right-hand side actually can look like some non-zero function of t. So that's going to be sort of our guess and see if we can work it out. So what we're guessing here, to reiterate, is that we think maybe we can find a solution to NH, the non-homogeneous equation, that looks like yp of t equals some function we'll call v1 of t. Instead of c1, we're going to do a function of t, v1, times y1 of t, plus v2 of t, y2 of t. And these y's are also linearly independent solution. They're the same y1 and y2 from up here. They're solutions to h. Okay, so these are the things that we can find using the characteristic equation method. So just like we were able to pick a particular C1 and C2 if we had some restrictions on it, like an initial condition, or we were able to do the uh, undetermined coefficients, again, if we had some restrictions on what the right-hand side equaled. If we have some restrictions, maybe we'll be able to solve for V1 and V2. So to think about what those restrictions would need to be, let's plug this in. Let's plug our YP into our equation NH and see what's going to happen. So the first thing we will need to do, as I just wrote, is calculate the first derivative of YP so that we can plug it in. And so since we don't have constants, now we have functions of t, our derivative is going to be a lot uglier than it was before. So let's just work it out. We'll use product rule. So we have yp prime of t equals v1 prime y1 plus v1 y1 prime. So that's product rule in the first term, plus v2 prime y2 plus v2 y2 prime. And then I can group these. I'm going to group these this way. I'm going to group the one that has the derivatives of v together, and then the ones without derivatives of v. Because remember that v1 and v2 are unknown. We know y1 and y2, but we are trying to guess what v1 and v2 might work. And remember, we're looking for some restrictions on it. So it's sort of a pain to have to take derivatives of a function that you don't even know about, right? And, you know, we're just sort of guessing at this. So our guess here is going to be to assume this is 0. So that's going to do two things for us. I know it looks like really, you know, why can you do that? Well, we can do this because we're just guessing still. So we're guessing that if we just simplify this down, then it'll be easy to calculate, and it'll be easier to calculate. And if it works and it gives us an answer, then that's great. And spoiler alert, it will give us an answer, or else I wouldn't be leading you down here. So we're going to assume this term is 0, which is going to simplify our calculations an awful lot. And then remember too that we're looking for one particular solution to NH. Just one. There are like millions, infinitely many solutions to it, perhaps. And maybe there are some that have this form where this term is not equal to 0. But those aren't the ones that we're looking for right now. We're just looking for one. Because, as we learned in the last section, in order to get a general solution to the non-homogeneous equation, you need the, you know, C1 y1 plus C2 y2 plus yp, any yp, just one. If you can just find one particular solution, then you can get the whole family of infinitely many solutions. Okay, so it doesn't matter which yp we find, we just need to get one. All right, so now we can take our second derivative. So yp double prime, I can just worry about that second term in parentheses and do product rule again, and I get v1 prime y1 prime plus v1y double prime plus v2 prime y2 prime plus v2 y2 double prime. This was a 1 over here. There we go. And now we can plug in. So we'll plug into NH, and I'm going to pause and write this out. So that's what I get when I plug everything in. So I've written it a little bit backwards just for ease of seeing things. So I've got my f now on the left-hand side, and I'm plugging just y, p, and its derivatives into um, our equation. This term is what I just calculated up here. This term is from up here. That was my yp prime, and I'm ignoring that zero term. And then this was our assumption, our guess at the form of yp in the first place. So now I can simplify things a little bit by making the observation that I've got a whole bunch of a's and b's and c's times the derivatives of y1 and y2. So I'm going to group things that way. So here are the first two terms that I'm going to sort of walk through before I finish writing everything out. So I have pulled out for these terms right here, that gives me, I'm looking for all the ones that have V1, just a plain V1 in them. And so I've got those three right here. And there's one with an A, one with a B, one with a C. And I have mixed up forgot a double prime there. Okay, perfect. Now this term here, I'm looking for all the things with just V2 in them. And again, I get one with an A, one with a B, and one with a C. So what I'm left with is a couple A terms. And so I'm going to write this out. I've got an A, and then what's left? V1 prime Y1 prime plus V2 prime Y2 prime. We do end up with some derivatives of our unknowns, but we'll see if we can manage that. So these came from here and here. Okay, so that's everything. Now, what's nice about this formulation is that because y1 and y2 are solutions to the homogeneous equation, this equals 0 and this equals 0. So what we end up with is that v1 prime y1 prime plus v2 prime y2 prime will need to equal f from my other side here divided by a. And I can divide by a. We always have to assume that a is not equal to 0, otherwise we don't have the second order equation, right? So that's not a problem. So what we've got now is two requirements on our v's. This one here and this assumption that we made up here. So in summary, I guess I'll sort of put that off to the side so that we can see it, although it's small. So in summary, if we can find equations that satisfy the two restrictions that I have circled in green over on the right, we've got y1 v1 prime plus y2 v2 prime equals 0, and that's this one right here. I just wrote it in a different order. And y1 prime v1 prime plus y2 prime v2 prime equals f over a, which is this one here. All right, I just innocent error. I don't mean equations. I mean functions. If we can find functions v1 and v2 that satisfy these equations, then yp equals v1 y1 plus v2 y2 will be a solution to NH. Okay, So that's what we're after. If we can solve these things, then we've got our particular solution that we're looking for. And so what's nice here is that, um, I said before that we didn't really want to worry about taking derivatives of a function that we didn't know. But what you'll notice here is that you only have derivatives of the unknown functions. So really, it's really like we don't have derivatives. We just have to find the v1 prime and v2 prime, and then we can antiderivative it and find our v1, v2. So that's kind of what makes this work here. So these are two equations with two unknowns, and you can do some algebra and or Kramer's rule, which I am going to skip because it's not a thing that you're ever going to need. Well, you might need to do it. We'll get to that in a second, but the point is that we can solve it. So if you do some magic, we will get these two explicit formulas for how to calculate V1 and V2, which are these. So of course there's an integral because we end up with doing that antiderivative that I just said. And I'll just write them out. All right, here they are. So these look gross, but I mean, you're just plugging things in. So all of these things are known. So everything is known here on the right-hand sides of these equations. Right, what do we have in these formulas? We've got f of t, which is given by the equation, y1 of t, y2 of t, which are the solutions to the homogeneous equation, and we know how to find those, and then a, which is, again, given by the equation. And we know we don't have a problem with dividing because we know a is not equal to 0. So this is the same denominator in both of these terms. It's just the numerator that changes. And so this is also not equal to 0. And why is that? Because y1 and y2 are linearly independent. And that result, that this quantity in the brackets is non-zero if y1 and y2 are linearly independent. That's something that we saw in the existence proof a couple sections ago. And so you see why this concept is super important and why everything relies on finding these two linearly independent solutions. Okay, so this is the method. This is the method of variation of parameters. So let's summarize. So here's what the method is. In order to find a particular solution to NH, or non-homogeneous equation, step 1, find two linearly independent solutions to H, the homogeneous equation. Step 2, solve for V1 and V2 of T. And you can use this either using the explicit formulas or using the conditions. So you can, sometimes it's going to be easier to go up and just plug these things in and just work out the algebra with the particular functions or with the functions that you have. So we can call this, let me call this variations VP, I'll call them VP conditions, and then I'll call these VP formulas so that I can refer to them down here. So in step 2, we are going to solve for V1 and V2 using either VP conditions or VP formulas. whichever is easier. Um, so the point is really, though, that you don't have to memorize these formulas up here. And then step 3 is your particular solution is given by the formula yp of t equals v1 t y1 t plus v2 t y2 t. So you've solved for v1 and v2 and then just plug them into this formula here. So I know this is a lot, and this method is really a bit cumbersome, which is why we've got undetermined coefficients, because that's really the preferable way to do it. But the issue is that the right-hand side doesn't always fall into those forms that we can use undetermined coefficients on. So let me do an example, and once you have an example, things are a little bit, hopefully, a little bit easier to work with. So we'll do an example, and then that'll be it for the video. So here's our problem: y double prime plus y equals tangent of t. So tangent is uh, an example of a function that doesn't fall into one of our categories that we can use um, undetermined coefficients for. So that's why we know that we've got to use variations of parameters here. So step 1, we'll solve this homogeneous equation. And you've hopefully by now done this like a gajillion times. And so this should be pretty quick. We get r squared plus 1 equals 0 for our characteristic equation. And then our solutions are going to be r equals plus or minus I. So then our y1 and y2 are remember, e to the alpha t cosine beta t and e to the alpha t sine beta t, blah, 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 blah. Anyway, in this case, it's just cosine t and y2 equals sine t. Okay. So step 2, solve our variation of parameters conditions to get v1 and v2. So what are those conditions going to tell us? Well, let's go grab them. So here are my VP conditions from before. And so now I'll just plug in my y1 and y2, my cosine and sine. And so we get this. So now I've just plugged in cosine and sine in for y1 and y2, and then over here, this is f over a, because f is the right-hand side of my equation and a is the coefficient over there. It's just 1. So now you could solve this. That works. It's not too hard. The other thing you can do is, take these formulas, and I'll show you something neat about this particular example. So, the other option that we had, instead of solving these conditions, we can plug in into VP formulas, which I've copied and pasted right here. And notice that this denominator here looks like, well, let's do it this way. Let's see, this denominator, do it in yellow. Denominator, I have no idea if I'm spelling that right. Whatever. Is y1 a times y1 y2 prime minus y1 prime y2, right? And so that's equal to, in this case, that's equal to 1 times, what's y1 was cosine, so we have cosine t times y2 prime is cosine t minus y1 prime is negative sine t and y2 is sine t. So that equals cosine squared of t plus sine squared of t, which equals 1. So cosine and sine are really nice functions to work with, in particular in this example. So that means that using these formulas is actually super easy. So then we get that v1 is equal to the integral of f, let's see, negative f times y2. So we get negative tangent t times y2 is sine dt. And tangent is sine over cosine. So this gives us negative integral of sine squared t over cosine t dt. And then similarly, v2 uh, equals the integral of, so now we've just got positive tangent t times b, or y1, which is cosine t dt. And again, we've got sine over cosine times cosine, so the cosines cancel out, and we get the integral of sine t dt. And so that integral is negative cosine t. We'll come back to the v1 integral in a second. That one's not obvious, so that's why I skipped it. We don't need to worry about the plus c because we just need a v1 and a v2 that satisfy these things, and we have one. Anyway, I guess I can come back to this one. This one you can just use an integral table, or you can use Wolfram alpha or whatever. And it is, well, so, okay, I think in my notes I wrote this out as sine squared equals 1 minus cosine squared of t. So then this integrand equals, I'm going to flip the sign here, and so that I don't have that. So my first term is cosine squared over cosine. So that's just cosine. Minus 1 over cosine, which is secant dt. And then you can use your integral table. So our first term is going to be sine t minus the secant one is an ln thing. ln of secant t plus tangent t. Sorry, I could have organized all this a little bit better. Anyway, that's how we do it. So we've got our answers for our v1 is this thing right here, and our v2 is this one with a negative. So now our step 3 is basically our answer. So we just plug in what we got. Yp of t equals v1 y1 plus v2 y2. So that's v1 is sine t minus ln secant t plus tangent t times y1 was cosine t plus minus, I guess, cosine squared, or cosine times sine. And then we can simplify this down a little bit. This quantity on our interval, so this quantity is 1 over cosine plus sine over cosine. So it's equal to 1 plus sine t over cosine t. And on negative pi to pi, or sorry, negative pi over 2 to pi over 2. On that interval, cosine is always positive, and 1 plus sine is always positive. So this whole thing is always going to be greater than 0. And so that's one reason why we have an interval. So I forgot to say on negative pi over 2 to pi over 2. That's one reason why we restrict to this integral, because if we once you get to pi over 2 or negative pi over 2, then your cosine is negative, or cosine equals 0, and so you've got just a discontinuity here, and you've got a problem, and that runs into this all sorts of nonsense. But we're not concerned about that right now. If we're just restricted to our interval, then everything's going to be nice and continuous and well behaved. So anyway, because this is always positive, we can get rid of those um, absolute values. And so then this simplifies down to um, sine t cosine t minus ln of secant t plus tangent t times cosine t minus cosine t sine t. And so those two cancel, and you're left with just that middle term. So that's negative cosine t ln of secant t tangent t. Okay, so that is our answer because we were looking for a particular solution, but we're going to do a bonus fourth step, and we can find the general solution to the problem. And that's always going to look like y of t equals c1 y1 plus c2 y2 plus yp. Okay, so that's really, this is a super important thing to say. And in this case, this is going to be c1 cosine t plus c2 sine t, the things we got in step 1, plus the yp that we just got here. So it should have been a minus cosine t ln secant t tangent. Oh, plus. I forgot plus is all over the place. Plus tangent t. And that is an even better answer than the one we were originally asked to find. Okay, so that's how you use variation of parameters. And hopefully the homework problems won't be too difficult, but this is, I don't know, it's just what it is. So have fun.